Okay, so Paul Chaignon from Orange Labs. I'm an R&D engineer at Orange Labs. I just accepted a permanent position there, so I was a fixed-term position before. So I'm going to talk today about how we can have an extension mechanism for Open vSwitch using BPF. Yeah, okay. Okay, so a word of warning before. So this talk is not about a new way to receive packets inside Open vSwitch. So conversely with the previous talk and the next talk, it's not about this. It's about how we can extend Open vSwitch at runtime in order to support new protocols and run new actions, for instance. So work around extending Open vSwitch has been the subject of a lot of papers in academia. So you can find a lot of papers with different approaches to extend Open vSwitch with new protocols, new actions, etc. So a few examples I want to give you of why we want to extend Open vSwitch and what we could do with an extensible Open vSwitch. The first one is probably the most recurring one, the most common use case that we're talked about. It has to do with layer 4 load balancing. So in a lot of cases, you want to use some layer 4 load balancing algorithm that Open vSwitch doesn't support yet. And the way we do this currently in production, in our case, is we already have an Open vSwitch in front of our virtual machines, but we send packets to some other process, or even in some cases to some virtual machine, in order to run the load balancing algorithm, and then send the packets back to Open vSwitch. And that seems kind of wasted, because we could actually use Open vSwitch to run the load balancing algorithm directly in Open vSwitch if we were able to express it with an Open vSwitch extension, for instance. So one other use case is the primary use case that we had when we started this work. We wanted to have a way to do fine-grained monitoring of our network. So for instance, if we want to debug some issue, or if we want to collect performance metrics for our network, we might want to collect per flow statistics at our software switch. And if we want to do this with Open vSwitch currently, we have to define a large number of different open flow rules, one for each flow. And the issue with this is that if we define one open flow rule per flow, we're actually going to lose any benefit from the mega flow cache, because we're going to have one rule per flow, and that's the same as the micro flow cache. So any benefit from the mega flow cache is lost in doing so. So we would like to be able to collect, for instance, per flow statistics, or counters or anything like this, and aggregate them, sending them back to the control plane. So obviously, one other thing we could do with an extensible Open vSwitch is experiment with pretty much anything. So recently, I had one of my colleagues working on LTE protocols who came to me asking if we would be able, with what we were working on, we would be able to match on GTP v2, on the GTP v2 protocol, and in particular on the TID field of that protocol. So he just wanted to do that very simple thing, and currently he has to implement a new kernel module in order to modify Open vSwitch to experiment with this and match on this particular field. So that one last example is probably not the best example, because if Open vSwitch is going to support P4 in the future, we could actually match on any kind of field, on any kind of packet field in any way we define them. But if Open vSwitch is going to support P4, it's going to have to support programmable actions as well. And what I'm going to present today is probably one way to implement these programmable actions from P4 in Open vSwitch. So in summary, I went over the motivations. I'm going to briefly describe you what we're actually trying to do here. And then, Okay. I'm then going to go over what I think is the main problem we have today with an extension mechanism for Open vSwitch, what we have to solve, and a few solutions from academic papers and from our work. So I'm going to go over the SoftFlow approach, and then the OCO work we did, as Ben mentioned, and the more recent work on OCO again, where we use the BPF verifier this time to try to solve this issue. So what are we trying to do now here? So what we want to do is have programmable actions. So for instance, in this case, I'm going to have one table with two programmable actions, alpha and beta. These actions are actually arbitrary programs, and they can write to arbitrary offsets in the packets. They can also access data structures that persist from one packet to the next. And therefore, we can take actions not only on one packet, but on what happened before. We can collect statistics. We can rewrite packets to do pretty much anything at this stage. So we want to be able to load these actions, these programmable actions, into the switch and use them in combination with other types of OpenFlow actions, such as in the second row of this table. So what's the issue with this? In the SoftFlow paper, they mentioned it as the non-determinism of these programmable actions. So in order to understand this, we have to look at how the caching mechanism of OpenVSwitch works today. So in OpenVSwitch, if we consider two tables here, in the first table, I'm going to match on packet with the source IP address of 10.0.0.1. If it matches, I'm going to change that source IP address to 10.0.0.2, and then go into table 2 and match again on the source IP address. So if a packet comes in with source IP address of 10.0.0.1, I'm actually going to run through these two tables, and I'm going to install a rule in the cache saying that if I receive said packet, I'm going to change the source to 10.0.0.2, and then send it out port 1. So that's pretty simple in this example. Now, if I change the set source action, and I use a programmable action instead, OpenVSwitch doesn't know what that action is actually doing. So it might change any field in the packet, but it might also not change any field in the packet. So if I do the same as I previously did and I install the rule in the cache, in this case, I might say that if the action doesn't do anything, then I'm going to go to table 2. I'm going to match on the second rule because the source IP address did not change. And I'm going to send the packet out port 2. But now if a second packet comes in and matches the rule in the megaflow cache, I'm going to execute again action alpha. Action alpha might this time change the source IP address, and if it changes the source IP address to 10.0.0.2, then my second action is not correct anymore. I should have sent the packet to port 1. So what we actually want to do here to solve this issue is we want to recirculate packets every time we execute a programmable action, because we don't know whether the subsequent actions are still valid or not. So of course, if we recirculate packets every time we execute a programmable action, we're going to have a very high overhead because we have to go through the full implementation of the tuple space search classifiers in user space. And that's very costly. So we want to avoid this as much as possible. So in the SoftFlow paper, the first approach I'm going to discuss, they use inputs from the developer in order to try to reduce the number of cases where we're going to recirculate packets where we shouldn't have. So what they did is they let the developer in the programmable action set an sfcoalesce metadata variable. It sets it to indicate whether a new lookup is required or not. So in this example, the same example as before, if programmable action alpha changed the source IP address to 10.0.0.2, then I'm going to set sfcoalesce to false in order to recirculate the packet. If it did not change the source IP address, then I can set sfcoalesce to true, and I can just execute the second action and output the packet to port 2. So this works well, but the issue is the developer of the action has to know a lot about whether or not it should recirculate packets. And that's not always obvious, because whether you should recirculate the packet does not only depend on what your action is doing, but also on what other rules you have in your tables. OK, so before I continue with the next two approaches, I'm going to give a bit of word on BPF, because we use it next. So the talk is OpenVSwitch extensions with BPF, but I haven't talked about BPF yet. So BPF is, as it was previously presented, is a bytecode that's used in the Linux kernel to define small extensions, basically, to the Linux kernel. You can use it in a number of cases in the Linux kernel. And one of the things it does, and what interests me here, is that it provides fault and memory isolation in software for your BPF programs that are running inside another program in another process. And so the benefit of doing this in software instead of using the hardware MMU for the isolation is that you can actually have a very lightweight exchange of data between your BPF program and the rest of your process. So for instance, if you want to exchange a packet between the two, you don't need to do a packet copy to cross the memory boundary. You can just address it. Now the way it does that is in part using a static analysis step that is done by what is known as the verifier, the BPF verifier. And the BPF verifier actually does a number of different things. So first, it's going to check whether the control flow graph for your BPF program is cycle-free. And it does so to prevent any infinite loops, obviously, but also to make sure that it can actually do the subsequent analysis. Then it's going to walk through all paths through your control flow graph. So that's a lot of paths through the control flow graph potentially, and that's why it has a few limitations as to the number of branches, for instance. And it's going to check all memory accesses in all of your different cases, so all of your different paths. In order to check the memory accesses, it's going to infer the basic types for your registers. So for instance, if it's going over a given path, it might determine that register 0 actually points to the packet, and register 1 actually points to the stack. And so those are two different types that you could have for our registers. Then using those types, it's going to verify every accesses to memories using the boundaries for instance, the packet. So it's going to check that the packet is at least as big as you need it to be for that memory access. And then, of course, it does a number of other verifications on instructions extra. So why BPF? There are a number of other isolation mechanisms that exist out there. So obviously, you might have heard of WebAssembly that's used in web browsers to provide this kind of isolation. There's also XFI that was a paper from a few years ago. It's used by Microsoft to isolate drivers into the Windows kernel. There's a Rust plus LLVM if you want to use it. There's native client in the Chrome browser. But the main difference between BPF and the others is, well, it's already used in the Linux kernel to do pretty much what we want to do here. So matching packets, writing the packets, filtering packets, etc. It's also supported by LLVM and Clang, so you can write BPF programs before in C and then compile them to BPF bytecode, so it's much easier to write. And you have a minimal set of instructions and minimal instruction set, and the capabilities of your programs are quite limited. And they're limited to the kind of use cases that we want to apply them to, so that's pretty good for us. The whole BPF infrastructure, we've re-implemented it in user space for work, and it's no more than 2,000 lines, including the verifier to check programs. Now, there's also a very low runtime overhead because a lot of the work is done at load time by static analysis to prevent any runtime checks, to avoid any runtime checks. OK, so in our second approach to address the problem I was mentioning before, we took a rather drastic approach. We prohibited all writes to packets. So to do so, we actually changed the BPF verifier to simply reject any program that has packet write instructions. So once we've done this, the packets can't write to the programs can't write to packets. So we made them match fields because that seemed a better match, and we made the programs return either 0, 1 to either match the packet or not match that packet. So for instance, in my example table here, if program alpha matches the packet with destination IP address 10.0.0.1, I'm going to send it out port 1. If it doesn't match, I'm going to continue the lookup and send it out port 2. So we had to do a number of other optimizations to work with this, with the Megaflow cache, but it works to some extent. But the issue is it's very restrictive. So obviously, in a lot of cases, you actually want to write packets. And so that's a very common need, and we actually prevent doing so with our approach. And even if you do not want to write a packet, in some cases, the binary output is very limiting. Because, for instance, if you want to do a load balancer, you're going to have one BPF program per output destination, per output port, sorry. So in this example, you will have a large number of different BPF programs to match in these cases. So recently, we took a step back and tried to look again at the BPF verifier and what it already does. And with the BPF verifiers already knows when a program is writing to packets. So that's what we use to reject programs that write to packets. So we could very well recirculate packets only if the program is known to write to packets. So we know that potentially it needs to be recirculated because it changed the fields of the packet on which we're going to match. No, this approach has no measurable overhead because we don't actually change anything compared to what I'm going to present next. But the issue is, in a lot of different cases, a program may have an instruction to write to a packet, but it may not actually execute it for every single packet. So in a lot of cases, you may, I don't know, write to the packet only in some specific case. And because of that, we are going to recirculate all packets where we don't need to. So the second approach we took, we tried to do a bit more work at the BPF verifier. And this time, we had the BPF verifier rewrite whole packet write instructions. So we modified the packet write instructions to compare the bits to which we are going to write in the packet with the bits used for the megaflow match. If there are bits in common, we know that we're very sure that we need to recirculate the packet because we changed the fields on which we matched to execute the subsequent action. No, because of this, there are some additional overhead for all packet writes. So if we have a large number of packet writes in our actions, obviously there's going to be some overhead. If we only have one write and we're doing other stuff, it's going to be lighter. The second thing is we're going to need to track bits used for megaflow match. So you might be wondering, why do I need to track bits used for the megaflow match? Because I already know that, for instance, in this case, in my megaflow cache, I have a rule matching on 10.0.0.1 and port 80. So I'm using these bits and these fields to match the packets. But actually, in this case, if action alpha changes the destination IP address, it's not an issue for me. I don't need to recirculate packets. I only need to recirculate packets if I change the destination port. So we have to track the field used to match packets after the programmable action was looked up. To sum up, we try to address the issue of programmable actions and the fact that they require some slow path lookups and diminish the number of cases in which we're going to recirculate packets. So I went over a few solutions. In the first one, the developer tells Open vSwitch whether a new lookup is necessary, and so we rely on knowledge from the developer. In the second one, we actually prohibited all packet writes. And then I looked at two cases where we rely on the verifier to do some of that work for us. So there are a number of open questions, of course, with this work. So we'd have to determine what kind of control plane protocol we want to use to manage programs. So for instance, currently we use the OpenFlow protocol, which we extended with a few new messages. But we could probably use the same protocol as would be used for P4 if it's supported in the future in Open vSwitch. We have to determine whether we want to use the BPF VM in the Linux kernel or user space BPF VM, but that probably mostly depends on the previous talk and the next talk and their results. And then there are a few other cases, like we need to determine whether programs should take the raw packet as an argument or maybe the data structure that represents that packet. And I'm planning to send an RFC patch set on the mailing list for the first approach I mentioned before. Thanks. I'll be happy to take questions and suggestions if you have any.
If you have a question, please come to one of the microphones.
Thanks for the talk. That was interesting. So the verifier exists as a security mechanism before programs can be loaded into the kernel. And so it seems like you're dependent then on the verifier to pass information to the kernel module and, when the verification process was happening.
Yep.
How are you thinking about making those changes to the verifier itself? Would you work with the upstream about making it extensible, or have you given that any thought?
So that depends a lot on whether we use the Linux kernel BPF VM or a user space one. At the moment, we're using a user space BPF VM, so it's a lot easier, of course, to prototype it. If we're going to use the Linux kernels one, it's probably going to change what we could do. So for instance, the last solution requires a lot more changes to the verifier, and it might not be acceptable in the Linux kernel. I honestly don't know. But the previous one, we only need to know if the packet is writing, the program is writing to the packet. So that's pretty easy to do, and it's probably something we can easily have some from the verifier. I think Netronom already does some changes to the verifier for this kind of stuff. So it depends a lot on whether we're using the Linux kernel BPF or not.
Makes sense. Great. Thank you.
We have time for another question if anybody would like to come up to one of the mics.
Hey, this is Shabazz. So one thing that I was a bit confused about in this thing is, first of all, it's an interesting talk. But do you know what kind of actions you are relying on for doing this recirculation? Because if it's just a set field action, you can lazily evaluate that in the slow path and then just generate a new megaflow entry for that. Why would you say you have to go back because you don't know the outcome of that action?
I'm not sure I understand the question.
So the thing is, for example, if your alpha action is a set field action, modifying some header field, can you not just go in the slow path and evaluate it and see based on that what other tables have to be composed together to generate a megaflow?
You mean for every packet going to the slow path to execute the action? Yep. Won't that have a lot of overhead?
No, not for everyone. Just like in a static set field action. You go to the slow path, you say, okay, I modified some field, and later on some table was matching on it. So you generated a composed one megaflow cache entry, and then you start using that for every following packet.
Okay. But I still need to recirculate packets afterwards.
Why would you have to do that? I think that's the confusing part for me. Because for stateful actions, it makes sense. But for some actions which are pretty stateless, modifying a field, I wasn't sure why would you have.
If you modify the fields in a packet, the subsequent actions might not be correct anymore. Like, oh, you mean executed during the slow path lookup?
During the slow path, yeah.
Yeah, I guess, yeah. Not sure. I probably can discuss it again. Not sure I understand all.
We have another question?
Yes. So, yeah, thank you. So do you find, I have comment about using verifier as a result to determine whether the field is right. So I guess verifier is doing static analysis, right? So I guess at runtime, you might detect a program that does right, but then actually at runtime, it doesn't do any packet field modification, right?
So
So it's more like very conservative, like you have verifier analysis all the branches, right? And if one branch has right, then you consider this program need to do recirculation. But at runtime, probably it's not going to that.
So those are actually the two different approaches I was mentioning. So in the first approach, okay, in this approach, we're actually going to do this in the static case. So we're going to recirculate packets every time we detect a packet write anywhere in the program. So that's the static case. And then the dynamic case is when we rewrite the packet write instructions. So this actually means that we're going to verify whether we need or not a recirculation at runtime with additional code.
I see. Oh, thank you.
All right, let's thank our speaker.